Okay, so far we've talked about how to calculate pH of strong acids and bases, and those are very simple because if you have a strong acid or a strong base, it ionizes completely. So if you have the concentration of an acid, you have the concentration of hydronium, which you can just simply plug into the pH equation. Same thing for strong bases. If you have the concentration of a strong base, you have the concentration of the hydroxide ion, which you can just simply plug into the pOH equation. We've also talked about how you would calculate the pH of a weak acid or a weak base, which involves doing an ice table because you don't know how much hydronium or hydroxide will form in the solution just by looking at the concentration. So with those types of problems, you are looking at what the weak acid is doing with the water, or you're looking at what the weak base is doing with the water, so a hydrolysis reaction. Now, if you were to put an acid with a base, that is different because it's a neutralization reaction. So in this example, we're going to go over how to do calculations for titrations with strong versus strong. And then we will go over what you would do if you had a weak acid or a weak base in the next video. But this is just a simple strong acid with a strong base. How would you do the titration calculations? All right, so the first thing, you have to know what the net reaction is. Well, if we have a strong acid and a strong base, we're simply looking at the reaction between hydrogen ions and hydroxide. So a strong with strong, the reaction, the net reaction is always this. Well, an acid, so let's say hydrochloric acid, when it is put into water, it ionizes completely. It makes hydrogen ions and chlorine ions. Okay? Well, a strong base, when it's put into water, will make same thing, it'll ionize completely, making sodium ions and hydroxide ions. Really, within strong acid versus strong base, the only things I care about are this and this. Those are the things that react in a neutralization reaction for strong versus strong. And if I'll go ahead and write out the equation. Like the entire equation is this. Hydrochloric acid plus sodium hydroxide produces sodium chloride and water. Well, I know that this will be soluble. This is a liquid, so we can't just X that out. And these will also be soluble. Remember, anything with group 1 is going to be soluble, and so that's sodium, that would make it soluble, that would make that one soluble, and hydrochloric acid is also soluble. So really, we have the ions that are broken up, so I'm making my net reaction. So if it's soluble, we're going to break it up into ions. Same thing for the sodium hydroxide. And then on the product side, I have NaCl, that will be broken up as well. And then water, which can't be broken up, it's a liquid. All right, so anything that appears on both sides, get rid of it. This goes, and then what we're left with is the net reaction of this. This is always the net ionic equation when you have a strong acid plus a strong base. This is always the net ionic reaction when you have a strong versus strong. All right, so our reaction is this. H plus hydroxide produces water. All right, so I want to know the pH at several times of this reaction. So 50 milliliter sample of 0.3 molar hydrochloric acid is being titrated with 0.2 moles per liter of sodium hydroxide. Calculate the pH before any base is added, okay? And then when 20 milliliters is added, 40, and then 75, and then also 100. All right, so When we have this type of problem, okay, before anything is added, it's pretty simple. So we know that we have a strong acid. We're starting off with our hydrochloric acid, and that's strong. So I have the concentration of the acid here before anything is added. Well, then that means that my hydronium, or my hydrogen concentration, remember it's the same thing, is also equal to 0.3. So before anything is added, it's going to be the negative log of 0.3, because that is the concentration of hydronium when you have hydrochloric acid. You have the concentration of a strong acid, then you have the concentration of hydronium or hydrogen ions. And this is before you've added any base, so something that we've done before. All right, so when you do that, negative log of 0.3, you're going to get 0.523. All right, so we have our pH of 0.523. This is before anything is added. Well, after we start adding bases, then what we're going to have to do is we're going to have to do a BCA table. All right, so when you have a titration problem and you're trying to figure out the constant or the pH as you go, you're going to do a BCA table. A BCA table these are for titrations, is very similar to an ice table, except we will not be looking at concentration here. We're going to be looking at moles. So anytime that we do a BCA table, we're going to have to convert everything into moles. The other thing about a titration problem is that the volume changes as you go. So if I'm looking for pH, pH is equal to the negative log of the concentration of hydronium or hydrogen ions. Well, this is the concentration. Well, if my volume changes, I will have to figure out what the concentration is after that volume has changed as well. All right, so let's do the first one. After 20 milliliters is added. All right, so I know my reaction is this. That's the net ionic reaction every time we have a strong acid plus a strong base. Okay, so we're going to do a BCA table. So before, the change, and what it is afterwards, but we use moles for this. For the ice tables, we just use concentration. All right, so before anything is added, we need to know how many moles of hydrogen, how many moles of hydroxide we have. We're not really going to pay attention to the water here. All right, so for hydrogen, I know that I had 50 milliliters of a 0.3 moles per liter. Well, I need to figure out how many moles this is before anything else is added. So we have 50 milliliters, which is 0.05 liters. And we're going to multiply that by the molarity because we need the number of moles. All right, so this times this will give me 0.015 moles. Okay, so we have to do the same thing for the hydroxide. So before we add them together, we have 20 milliliters of this. We're going to add 20 milliliters, and the molarity is 0.2. Okay, so we have 20 milliliters. We're going to convert that to liters. That's 0.02 liters. Multiply that by your molarity. All right, so this times this, I will get 0.004 moles. Okay, so this is basically another form of stoichiometry, honestly. So when you're looking at this, you're going to have 0.015 moles of hydrogen plus 0.004 moles of hydroxide. So you're going to have something that gets used up and something that's left over. Well, since everything is a 1-to-1 ratio, the amount that is smaller will get used up. So when you calculate your number of moles, subtract the smaller number. This is a smaller number. Hydroxide will get consumed in this reaction. So I'm going to take away 0.004 from both. All right, so this minus this will give me 0. This minus this will give me 0.0011. All right, so it was asking what is the pH after you've added the 20 milliliters of hydroxide. Well, this is what I have left over. I have hydrogen ion moles left over. So now what I need to do is I need to solve for pH is equal to the negative log of hydronium, which remember is the same thing as hydrogen. But I can't just simply plug it in as 0.011 because this is the number of moles, not moles per liter. So I have this many moles. I need to divide that by the volume. Well, it's not 50 anymore because you added 50 to 20 milliliters of hydroxide. So your actual new volume is actually 70 milliliters. So it's 0.05 liters plus the 0.02 liters. So you have to find the new volume when you do this because the volume is changing. Every time I add some more base, my volume changes. So once I do that, I'm going to get 0.157. And that is my concentration. So now I can plug it into my pH equation. That's equal to the negative log of 0.157. So my pH is now equal to negative log of 0.157, 0.8. So my pH went up a little bit. All right, so now let's look at the next part of the problem because it says how much or what's the new pH when you add 40 milliliters. So we're going to do the same thing again for 40 milliliters. All right, so we have our hydrogen plus hydroxide produces water. All right, so we're going to have to figure out the number of moles first. All right, so again, we started off with 50 milliliters of this, and my molarity was 0.3. And now we're going to do it for hydroxide for 40 milliliters. All right, so 50 milliliters is actually 0.05 liters. You're going to take that, multiply that by 0.3 moles per liter. You get 0.015 moles. All right, so now I'll do the same thing here. You're starting with 40 milliliters or 0.04 liters this time. All right, so when I do that, I'm going to get 0.008. All right, so now, again, hydroxide ends up being smaller here. So the change, it will get consumed, so we're going to subtract out 0.008. Since everything is a 1-to-1 ratio here, this will get consumed. I'm be left with 0 hydroxides. And then this minus this would give me 0.007 moles. Well, it's asking for the pH. And remember, pH, we have to have the concentration, not just the number of moles. So we need to figure out what the concentration is now. All right, so I have 0.007 moles. I'm going to divide that by my volume, but it's not 50. It's 50 plus 40 because the volume has changed since I've added more liquid to it. So it's 0.05 liters plus 0.04 liters. And then if I divide that, I'm going to get 0.0777. Now I can plug this into the pH equation. All right, so now my pH has gone up again, but only to 1.11. So remember, as we're titrating, the pH, goes up or down a little bit each time until we get to the point where the moles are equal. All right, so let's look at the next one. All right, the next one is 75. We're going to do 75 milliliters now. All right, so let's do a BCA table. All right, so initially we start off with 50 milliliters of the hydrochloric acid. And this time we're going to do 75 milliliters of my base. All right, so 0.05 liters times 0.3 moles per liter. It's 0.015 moles. And this will be 0.075 liters multiplied by 0.2 moles per liter. This will also give me 0.015 moles. All right, so I'm actually going to stop at this point because I can see my moles are equal to each other. So when this happens and it's a strong acid plus a strong base, my pH will be equal to 7. So when you have a strong versus strong, when the concentration of the hydroxide is equal to the concentration of the hydronium or the hydrogen ion, however you want to look at it, then you have met your equivalence point, which will be 7 when it's a strong versus strong. So really, you're looking at the pH of water because remember, your pH of water will be equal to 7 when the hydronium and the hydroxide are equal to each other. So our pH should be 7 here. All right, so let's look at the last part. I think it says 75, or I'm sorry, 100. So we're going to do 100 now. All right, so for this, it's still 50. And this will be 100 milliliters now. All right, so 0.05 liters times 0.3 moles per liter will give me 0.015 moles. All right, so now we're going to do 0.1 liters times 0.2. So I'm going to have 0.02 here. All right, this time the acid is less. So we're going to subtract the acid. So the acid will be 0 here. And then for the base, I will have 0.005. Okay, so this is for the hydroxide this time. So if I plug it into the pH equation, technically I'm going to get my POH, which is equal to the negative log of hydroxide. All right, so we still need the concentration. This is the number of moles, not the concentration. So I'm going to have to find that concentration first. So it's 0.005 moles divided by my volume. Well, it's not 50, it's not 100 here, it's 150 milliliters because we have combined them together. The new volume is 150. All right, so when I do that, so 0.005 divided by 0.15 will give me 0.333. And this is my molarity, but this is of hydroxide. It's not of my hydrogen ions now. So now when I plug it in, I'm going to get my POH. So my negative log of that will be 1.477. So when I subtract this from 14, my pH will be 12.5 roughly. And this makes sense. If I've got more hydroxide, my pH should be above 7 at this point. So whenever you do a titration problem, your reaction, it will be this, if it is strong versus strong. So this is your net ionic reaction if it's strong versus strong. You're going to create a BCA table. Okay? When you do that, you're going to solve for moles and the B row, before row. All right, once you do that, then you're going to subtract smaller number of moles. Then you're going to have your moles of hydrogen and hydroxide afterwards, and you will figure out, calculate the new molarity. Remember, volume changes as you add acid or base. Then plug it into pH. And then also with a strong versus strong, if your number of moles are equal to each other, your pH will be 7 at that point.